Welcome to the next lesson in the module on classes in Java. I call this lesson New Objects in Old Places because we are going to revisit a few concepts you are already familiar with and see how these notions apply to objects. For example, you are already familiar with arrays of primitive data types, but after you complete this lesson, you'll know how to create an array of objects. You'll also learn what happens when using the equals operator with objects, and recognize what happens when objects are passed as parameters to methods. Finally, you'll understand the static keyword. At the conclusion of this lesson, you will have deepened your understanding of classes and objects so that you are able to evaluate and determine how objects are used in familiar situations. Let's start by seeing how objects operate as part of an array. Once again, there are similarities between primitive data types and objects. We declare an array of primitive data types, such as int, the same way we would create an array of count objects. But again, we must rely on our new understanding of objects to keep us out of trouble. This first declaration creates an array of variables that will store ints. It is initialized to all zeros. The second declaration declares an array of variables that will reference objects. We can immediately begin using the array elements of an int array. But if we attempt to access the objects in our array, well, actually there aren't any objects in our array, just variables that can reference objects. Creating an array of objects is a two-phase process. The first line will create the array of references. Then we often use a for loop to create the objects where the field data will be stored. Then the data itself can be referenced. We just need to use constructors to create the objects to be referenced. We can create an array of objects using a single line of code, similar to the way we create and fill an int array. This code will create the array of the objects it references. And this code will create the object and fill them with data. Here we use two different constructors that accept parameters for the fields. What about using elements of these arrays with methods? Once you have properly created the array and instantiated each element, they are used and referenced the same as you would any other object. They can call their own instance methods, can be used as parameters, and can be printed using the default or overridden toString method. Let's examine an object as a parameter. Once again, we should rely on our understanding of objects. Let's review a primitive data type such as ints first. As a side note, these diagrams are all abstractions that help us to understand how objects work, without having to know absolutely all of the implementation details. When a method is called and an int is passed, what we actually pass is the value of that variable. The method may make changes to that value, but unless it is returned to the original variable, no change is seen or made to that original value. What happens when an object is passed as a parameter to a method in a client program, for example? We actually pass the reference to the object. This is known as pass by reference. The method can now access the actual object. If this method happens to change some value in the object, the change will be made to the object itself, not some copy of the object. When the method ends and the local variables are no longer accessible, the change to the object remains. This is very different from what goes on with primitive data types. Here is a common error seen when working with objects. This is a trap that you should easily avoid because you understand objects and how they work. We have an object that is passed to a method as a parameter. As before, this sets up a reference back to the original object. In the method, we create a new object and fill it with data that is copied from the original object. Then we make the desired change to the balance. And finally, we make the passed object equal to the new object, in hopes of making the balance change permanent. But the result is probably not what the programmer had intended. The local object X now references the new object, and when the method ends, it all goes away. Notice, no change to the original. The lesson? Keep it simple. Pass the reference to the object and make changes using that reference variable. One of the problems with the last example was trying to copy the data of one object to another using the equals operator. Although this works perfectly well for primitive data types, it's quite different for objects. Here we have two objects, account X and account Y. When we make one equal to the other, the effect is as it should be. They both now point to the same object. As it should be, but perhaps not understood by uninformed programmers. Now a change to account Y will also be made to account X, because in fact they are the same object, or they're referring to the same object. This will mystify the less informed, but not us. Setting one object equal to another is permissible in object-oriented programming, but be sure that is exactly what you want to do. If you really wanted to make a copy of an object, there are lots of ways to do it. Here's one way. In your class file, you may have a method to do the trick. The object that will be copied is the input parameter. The object that receives the data would be the implicit parameter. It takes more code, but this will make an actual copy of an object. Now we will address another issue. What happened to static? If you recall, all or most of our methods to this point in the programs we've used thus far have included the keyword static. In our class files, it's been missing. It has to do with how state and behavior are created when a constructor is called. Each object is built with its own set of instance variables and its own copy of all of the methods. That is because none of them have been declared static. So when would a variable or method be declared static? Let me build an example for you. Suppose we want to build account numbers by using the year, account holder's name, and a sequential number, something like this. This may lead us to define the account number as a string, which might be more practical than making it an integer. Thanks to abstraction, a change like this won't be a problem. Client programs use class methods to get and set the number, so the data type of this field doesn't really matter to those clients. Changing it should not have an effect on the client programs if they were written in accordance with good object-oriented principles. To build account numbers, we might write a method in our class like this one. This method would be private because it would only be used by the objects in the class, not the clients. Note, we've changed the type of the account number to a string. You can imagine we have other private methods to create the year portion of the account number and hash the account holder's name. This would then be concatenated with a unique sequence number that was incremented each time a new account was created. Let's look at the constructor class. We no longer want to allow the client that is invoking the constructor to supply the account number. We will create that ourselves. And we don't want a default constructor anymore, one that simply doesn't fill in any of the fields. This would enable clients to create empty or dummy accounts, and that would not be useful. Our improved constructors rely on the method to build a proper account number. We would also need to delete the setNumber method because we don't want client programs changing account numbers. How can we keep track of this sequential number? We need this to generate sequence numbers for the accounts. We could create it in the client programs, but it describes the state of the class and should therefore be included in the class. Every object needs to access and increment the same tally. This should be done each time an account object is created. Naturally, this count should be private. Only objects will need to access it directly. To solve the problem of a shared variable, we use a static field. It is declared in the class file, just like the instance variables. But using the keyword static, we prevent an instance from being copied into each object upon creation. The method that used this field will still be found in each object, however. An object of the class can reference this private static field directly, but they will be referencing the same field that all the other objects of the class are using. Each object accesses and updates the same count. We might want to create a constant or final field that is associated with the class. We would use public static final in that case. It could be accessed by clients because it is public. It is static, so there will only be one copy for the class. And the keyword final, as before, makes this a constant. It is accessed by the client using the class name, since it is not associated with any particular instance of the class. Objects of the class can access the constant directly. Finally, we might find it optimal to create static methods in our class. These method definitions would reside in the class, not copied to each object. We might create a static method if the method could possibly be called even if no objects had been created by client programs yet. Perhaps we want to see the current interest rate for all accounts. Calling the method requires that we use the class name. Another reason for creating a static method might be to reflect that a particular method, though part of the behavior of the class, uses more than one object. It may make sense to call it this way, again, using the class name. This lesson has itself been an excellent example of the value of abstraction and its many layers. We've learned just enough implementation details about objects to help us understand, not just memorize, how to use them with these familiar constructs. But we haven't bothered to go any deeper into notions of memory management, storage, and so on. As you continue to study, you may find it necessary to go further into some of these areas. And if you do, what you will find will not be conflicting, but will further illuminate what you've learned so far. In the meantime, we've got a little more to go in our lessons on classes. To gain more practice with the concepts covered in this lecture, make some changes to your client file. Create arrays of account objects and call some methods. Create methods that take account objects as input parameters. In the class file, create a static variable like the one in our examples. Change the constructors and test them by creating objects back in the client file. The more you practice and use these ideas, the more comfortable you will be with them. Now that you've completed this lesson, you should understand why objects act the way they do when they are used in an array, made equal to one another, or passed as parameters. You should also understand how to apply the static keyword to create variables and methods that are part of the class definition, but not stored in any single object. By knowing how to use objects in all of these situations, you can build more powerful code that is both correct and optimized for reuse.